So in all these levels of abstraction, we can bring about power awareness to the IC. So if we split the IC design into analog and digital, there are some techniques that are common to both these both these technologies, but there are some which are limited to particularly to the analog IC or digital IC. So also the main idea is to reduce the supply voltage for any of these devices, because as you reduce the supply voltage, the power consumed or the energy consumed and the end will be reduced. So that is the first and foremost thing that the engineers are trying to do to reduce the power consumption. So from that point, it comes like reducing the threshold of the transistors that are there in the IC, using multi-threshold devices, variable body biasing techniques, and you can reduce the frequency as such, so that the number of switching cycles are different for a given point of time, which reduces the overall power as such. And here I'll just give you a little idea on what is the type of power that is adding on to the entire power consumption. So it's basically dynamic and dynamic or switching power loss, and conduction loss, or in the static loss. All these are the losses that are that amount in total to the power consumption of the IC. So in the static power loss, that there is the leakage current that happens when the system is not switching, it is on, and at that time, if any leakage happens, it adds to the power consumption of the IC. And even if it is not switching, there can be conduction happening in the transistors, and that conduction can lead to loss. And the dynamic loss that we are talking about, that comes to a picture when we are talking mainly about the digital ICs, where the switching of the gates happen, and whenever there is a switching, there is a short circuit current that is happening between the high side and the low side transistors, which leads to power consumption. So there are different, these are the basic power consumption causes that happens in ICs, and there are all these techniques that are listed here, directly or indirectly amount to reduction of either of these power consumption to be reduced. So there are apart from the levels of abstraction, there are new technologies that are coming up for increasing the energy efficiency of ICs. So one among them is silicon photonics, where we use the optical technology to do our work, rather than using an age-old normal CMOS based or FinFET based MOSFETs. And in 3D ICs, the interblock connections between the ICs are optimized using wires rather than using powers and interconnects for reducing the overall power consumption of the IC. And there are several advanced packaging techniques that are being used, and also in research, where the high density packaging is used to enable increased memory, increased bandwidth, and during high power operations, but yet energy efficient systems. So these are the basic ways by which we make an IC power aware. Now let's so since our time and scope is limited, we can't see in detail about what are the causes of power consumption and how we can go about for each of these ways. But for this particular webinar, we'll be learning about a single technique that are widely used in ICs for having better power awareness. So the objective, let's say, is to design a chip that can sense the cardiac activity of a patient. And if any irregularities are identified, what it should do is it should send send an alert to the medical team or a doctor or anyone, so that they can take necessary action. You can think of a person who is at home, who is having a cardiac issue, cardiac related issue, and he's under medical care for a prolonged time, and he needs some kind of sensing on his cardiac activity, but he's not quite close to the medical attention team. So in that case, what we basically need, we need the sensor to sense the cardiac activity, and we need the signal acquisition circuit, so that whatever signal you're receiving from the signal is conditioned and processed so that it makes sense for the other end of the reception. So we need some memory also to store the data, and we need a controller which can which controls the operation of each and every single block of this entire cardiac activity monitor system. And obviously, we need transceiver modules to transmit the data that is acquired by the sensors to the medical team. So this can be a probable system that works well to achieve what we want. Here we have sensors like, so in our case, it's a biomedical sensor like an ECG or something. It can also be used for other applications, so let's not look into that. What we are concentrating is on a biomedical sensor application. So here we have data pre-processing module where the signal conditioning and signal acquisition is happening. We have a controller that controls all these different modules, who should talk, who should not talk, who should be working, and how it should be working. So for that, we need this controller to be on board on the system. And we have a memory where we store the data, obviously, and we have a transmission unit. Here in this case, we have, let's take a Bluetooth transceiver, which takes the data, which is processed by this signal conditioning unit, which is converted to digital domain by the ADC, and this data we are planning to communicate through this Bluetooth transmitter. Now, let's see what is the challenge in designing this. This is a battery operated device, because this is a wearable device that we're talking about. It has to be on the patient's body always, and whenever, because we don't know when this cardiac irregularity is going to come up. Whenever it comes, once it comes, it has to be reported as required. So it has to be a battery operated device, obviously. Now we know that since it's a battery operated device, as we were discussing before, since it's a battery operated device, it has to have some kind of power awareness to this. One system level technique that we can go about is duty cycled power profile. What is duty cycle power profiling? All the modules in the system will not be on always. Whenever you want a module to be functioning, you will switch on that module only at that particular time. So since it is not on the entire clock period, that's why it is called duty cycle. So it is on only for a smaller portion of the entire clock period. Let's say we have module A, B, C, D, E on this board, as we have seen here. So we have the sensors, all these module sensors to transfer modules. We have all these things. So let's assume A, B, C, D, E are all these different blocks. So at any point of time, I don't want all these modules to be on. They are on only when they are required, and that is how I have programmed my controller to basically switch on and off whatever is required or not. So these power duty cycles can be overlapping also. Like as you can see, there is a time where we want module C and D to be on, module E and A to be on. So it can be overlapping also. So what we basically do in power duty cycle power profiling is we define different modes: sleep mode, active mode, and transmission mode. So in sleep mode, the device is just on. It is not doing any kind of operation. It is just on. So this can be like a constant or the default mode in our particular SOC that we are discussing. It's just on until until there is no indication of the irregularity. It is just off. It's not doing any operation. Now in the active mode, what it does is it is processing the data. It is acquiring the data and it is processing the data. We are not sending it yet. So during this processing mode, the transmission modules like the Bluetooth transceiver unit is completely off, and only the data acquisition module and the controller is on. Now the moment it identifies that there is a irregularity in the operation, in the cardiac signal that it is receiving, what the controller does is it immediately starts the transmission mode, and in that mode the data is the Bluetooth device is made to be on, and the data is transmitted. So in this way, if we see, we can see that if we can see that the overall power consumption or the overall power consumption can be reduced, and it can, and we have brought about some kind of intelligence to the system that it has to be power aware. So let's see some numbers to get the feel. Like basically we have ADC, AFE, which is analog front end, a controller, and a Bluetooth transceiver. These are the main blocks that consume power in this system. And if you see what the power consumption, the 7.3 milliamps, the highest power consumption, as you can see here, is of the Bluetooth module, because always the communication part is what consumes the highest power in any system you take. And the active, and in the active mode, this AFE, ADC, and all will be consuming together. They'll be consuming around 600 microamps of current, and in sleep mode it consumes only 10 microamps of current, because most of the blocks are off. So as you can see here, the power when it is in sleep, it consumes lesser power, and in the next session, what happens is it's not transmitting anything, but it is active, so it consumes power related to only the active part of the system. And in the transmission mode, we have both the active and the transmission blocks are on, so this is where it consumes highest power. Now it sensed that in the last phase, as you can see, it sensed that there is the regularity that is happening continuously, so those modules are continuously on, so the data is continuously received, processed, and transmitted. So in this way, we can power profile a sensor device in order to bring about power awareness to the system. So as I was telling you, let's see some numbers, like the current consumption for the sleep and active mode of different modules are given here. So we have in sleep mode 10 microamps, in active mode we have 600 microamps, in transmission mode we have 7.3 milliwatt. This is at when we are transmitting at a rate of 1 megabits per second. So if this is the way that if let's say we have a system like this, then if you can power profile your entire design in such a way based on what is your module, what are all modules you have, and what are the current consumptions that individually they take. And you can also think like how much is your energy, how much is the battery capacity that you are going to use, and if you're using such a load to the battery, how long it can stay, and is it sufficient for the given battery capacity, or you will have to still work on reducing each of this power profiling plans. So these are the things that that we will be. So this is one way of doing the power awareness, but not the only one. There are different, as we have discussed before, there are the different levels of abstraction. This is one simple way of bringing about power awareness to the IC. In all the levels, there are a lot of techniques that are used in the industry to bring about this power awareness or energy efficiency to the system. Now let's see what an IC designer does in a day. So what you will be doing is initially we will be getting some specifications for. Let's talk in particularly about designing a power aware IC. So we have the specifications as we have discussed in the previous slides. I have a battery, and the battery capacity is already defined, and the application is already defined. Now we have to see for each particular what is the system architecture that you have to bring about, and which architecture will give more flexibility on defining the power profiles. So based on that, maybe sometimes you will get a reference circuit to start with, or there are no reference circuits, then you have to work on a system model where you will be using all the ideal blocks with considering that the world is perfect. And from that model, you will start designing the circuit and start defining. You will be getting the specs proper in this initial phase. Then from with that specs in mind, you will start designing the circuit. Then you will be doing simulations, lots and lots of simulations to see whether it works functionally well, whether it works with all the variations that can happen in the final fabricated IC. So keeping all this in mind, you will be really doing, so as an IC designer, most of your time you will be doing, what you will be doing are simulations. And once it is laid out, so for layout, basically in industry, you will have separate team who does the layout. Layout is basically how you, putting the physical, that's where the physical way of for realizing an IC comes in the layout step. Like you will be defining each of your transistor, each of your resistor, capacitor, all the elements will be defined in terms of physically metal pieces, like how long, how wide, how close, how far. All these factors are taken care in the layout phase, which basically is taken care by experts who does layout engineers. So after that, we have to do, after the layout also, we have to ensure that the performance and the specifications that we have are all matched. So we do post layout simulation as a circuit designer. So this is what you will be doing if you are an IC designer. Moving on to the tools that you will be using for these processes, Cadence, Mentor Graphics, and Synopsys are the industry giants who make the tools for you to design, to work on analog and digital ICs, or even mixed signal ICs. And in some cases, you can use MathWorks, MATLAB, or Simulink to model your circuit to get a feel. Like you can either do it in using a Simulink, you have the blocks and you model them, or in MATLAB you can make mathematical models of your system or circuits and see how it works. So here I have listed out some popular EDA tools that are brought about by Cadence, Mentor Graphics, and Synopsys. So each industry or each company follows its own design flow and tool sets. So wherever or whichever company you work for, you will have to have a hold on the design flow that they follow. So these are some companies, some semiconductor giants who work on basically on IC design and also particularly on power aware IC designing. So you will find yourself looking for job profiles like SOC power optimization engineer and power aware design verification engineer when you are particularly skilled in designing power aware or energy efficient ICs, which are basically intended for battery operated devices or systems. And if you see, so it's this power aware IC design or energy efficient IC design is not only a hot topic for the industry, it is also a very much trendy thing that's going on in research. Like once you have the power awareness, then it's very, that's the actually the bottleneck. The power is actually the bottleneck that is hindering the growth of research domains like flexible electronics, pervasive sensing networks. Like you have having a sensor network everywhere, literally. And even the implantable medical devices, like as you can see here, there's a pacemaker sitting inside a person's body. So it is actually implanted inside, and you cannot expect a battery to be sitting inside your body. Nobody will wish to have a pacemaker like that. I'm pretty sure about that. So here, research groups are working on harvesting energy from person's body heat, so that there is an energy harvesting system which harvests the body heat and operates this pacemaker. So in that case also, you cannot expect huge power for the circuits to operate on. It will be a very small energy that you will be harvesting in terms of microwatts to definitely less than 1 milliwatt of power. So your circuitry should be well equipped with techniques that can help it to make it work with this low power, uh, low energy availability. And uh, and also the thing that is currently that is going on in everyone's industry is AI and machine learning. So we also need accelerators that can work for the implementation of complicated algorithms for machine learning and AI. So even for that, we need energy efficient systems so that it runs on low power and it can run powerful and complicated algorithms. As well as the next phase of IoT is industrial IoT, where apart from having smart cities and smart homes, we're talking about IoT devices making entire cities or entire townships smart. So in all these cases, we need sensors and batteries for sure. So wherever sensors and batteries are there, wherever data is involved, we always have to worry about power awareness. So on a concluding note, the takeaway summary is that the power-aware IC design has huge business and research scope and value, and there is huge demand for skilled workforce who is aware of the techniques and technologies that are available or can be uh, can be molded to bring about energy efficiency in any circuit possible. And for that, to reach to that, you will have to have very good expertise on both the advanced technologies that are available as well as the tools that are provided by the EDA vendors who are really trying to bring about tools that are specifically used for power aware design and verification. And also this domain is highly dynamic, like it's still growing, and the demands are increasing every year by year, like the reduction in power or the constraint on the power budget is ever increasing. So it's the job of skilled engineers to bring about novel ideas and techniques uh, to achieve the targets that are imposed on by the industry. So with that, I would like to conclude the presentation. Thank you for your valuable time. Hope it helped you in some way.